Okay, we're going to kick off homework 2 for separations, part A. We're going to explain and derive the Rachford-Rice equation for vapor-liquid equilibrium, and we're also going to implement that in Python and basically explain how the bubble and dew pressures can be used to infer an initial guess for the vapor mole fraction, and apply that function to a flash calculation described by my professor. And for now, I'm going to get into the derivation. As I said, we're going to go ahead and explain and derive the Rachford-Rice equation for vapor-liquid equilibrium. We'll also be showing that it's a monotonic function of the vapor mole fraction, which is the vapor over the feed. That is this phi right here. And just an overall mass balance right here. We have the feed is equal to the liquid and vapor in the system. So that's our F, L, and V. And we can simplify the left-hand side by dividing by the feed. So we just have 1 right here equal to the liquid divided by the feed plus the vapor divided by the feed. And like I said above, this phi is that vapor divided by the feed. And then therefore the liquid over the feed is 1 minus phi. We can say for any species I, we have Zi times F, that's the composition of the feed, is equal to Xi L plus Yi V. Xi is the composition in the liquid fraction, and Yi is the composition in the vapor fraction. And then this Zi is just the overall composition in the feed. And again, if we divide by the feed, we get Zi on its own equal to Xi times L over F plus Yi times V over F. And we defined V over F as phi and L over F as 1 minus phi, so we can also write this in terms of phi. We can also define Ki, which is the equilibrium ratio of the vapor fraction over the liquid fraction. So now we can actually take this and get it in terms of x only, because we know that yi is equal to this Ki times Xi. So I'll just rewrite that Zi is equal to Xi minus Xi phi plus Ki Xi times phi. And then we can take out the Xi to further simplify this. We have 1 minus phi plus Ki times phi. Now we know that we can take this Xi and say that it is equal to the feed composition divided by 1 minus phi plus Ki phi. We can also do the same thing for y, so if we wanted it in terms of y, we could say Xi is equal to Yi divided by Ki. We would have Zi, I guess I'll do this in orange as well to keep it somewhat consistent. We have Zi is equal to xi, which is yi over ki, times 1 minus phi, plus yi times phi. And remember that this phi is the vapor over the feed. We can then multiply each side of the equation by ki, then we can again factor out the yi this time. And notice that this is the same as above. The only thing that is different is we have that ki term, so when we isolate yi, we have zi ki divided by the 1 minus phi plus ki times phi. And those are our two main equations right now. Something else we know is that the sum of all of the liquid fractions within a mixture should be equal to 1. The same thing is true for the vapor fractions. So for an example, I can say if we had benzene and toluene, the liquid fraction of benzene, if it was 0.7, then the liquid fraction of toluene would need to be 0.3. And then it's a similar thing down here. You just have to make sure that it's balanced and it adds up to 1. But that is just an example, so I'm going to get rid of that. Therefore, we can also say that the summation of xi minus the summation of yi is equal to 0 because that's 1 minus 1. And the same thing is true, it doesn't matter if you put yi first, it's still 1 minus 1. So what we're going to do actually is take the summation of yi and subtract the summation of xi, so the vapor mole fractions minus the liquid mole fractions, and we know that's equal to 0, and then we plug in what we circled in or squared in pink. Let me redo that summation, it looked horrible. So we have the summation of zi ki divided by 1 minus phi plus ki times phi. And we're subtracting the summation for xi, which was zi all over the 1 minus phi plus ki phi. And that is equal to 0. So subtracting those, we can write it as one summation where we have zi times ki minus zi. This is because they both have a common denominator. Same denominator down here that they both had. And then you can simplify it a little bit further by taking out this zi. And let me actually simplify this a little bit more. So we have 2 phi's, so I'm going to take that out, do 1 plus phi times ki minus 1. And this summation, like all the other summations, I just didn't specify. I'm terrible at writing summations, wow. They just look horrible, that's okay. These all go from I equals 1 till n. And this right here is actually our Rachford-Rice equation. So we derived the Rachford-Rice equation for vapor-liquid equilibrium. We also want to show that it's a monotonic function of the vapor mole fraction. So monotonic functions are always either strictly increasing or decreasing. You shouldn't have both occurring. So a good way to look at this is to take the derivative of the Rachford-Rice equation. So I'm going to notate this like as f prime of phi, which is the vapor mole fraction that I defined up here. So that would be d phi of our summation that we have up here. And to get this, we need to pay attention to our derivative laws. So I'm just going to have the summation like that for now. And we have the denominator times the derivative of the numerator. The derivative of the numerator is 0 because there is no phi located in the numerator. So we actually get rid of that term already. And then we subtract the upper numerator and take the derivative of the denominator. The denominator is our 1 plus ki phi minus phi. So the derivative of that would be ki. This would be a constant, minus 1. And then we divide by the denominator squared. This results in something that looks like this. We have a negative zi in the numerator. We have ki minus 1 twice, so I'm just going to square that all over our denominator, which is the same as before, it's just squared now. For all possible values of phi, since this denominator gets squared, the derivative will always be negative. So it does not have a chance to be positive. Therefore, this derivative is strictly decreasing, and so it is monotonic. Strictly speaking, it's a monotonic function of phi, which is the vapor mole fraction, if I can write an F. And basically the benefit of this Rachford-Rice equation is if we solve for the root of this starred equation, we can solve for phi. We could also solve for any of the compositions, so any of these three. And for our next step, we are going to jump into Python. The first thing we want to do now is to implement the Rachford-Rice VLE calculation in Python and check that the flash occurs in the two-phase region. We also are going to explain how the bubble and dew pressures can be used to infer an initial guess for the vapor mole fraction. We know that at the bubble point pressure, the phi, or the vapor mole fraction, is equal to 0, while at the dew point pressure, it is 1. And if our system pressure, for example, 1 bar, which we'll be doing later, if our system pressure is between the bubble and dew pressures for our system, then we are going to be in the two-phase region. And to get a guess, we could do something like this. We could do a linear interpolation, so taking the bubble pressure minus the system pressure divided by the bubble pressure minus the dew pressure would give us a decent estimate, at least to start off with. So yeah, that is for this piece, and now we want to implement what we derived earlier. So I already have this import that I've been using. I also took in the properties of my benzene and toluene. I'm going to go ahead and define our Rachford-Rice. And we know it's a function of phi, z, and k that we talked about before. This is the summation that we calculated before, which was z times k minus 1 divided by 1 plus phi times k minus 1. And as you can see, we are doing a flash calculation at 1 bar and 370 Kelvin, so this is isothermal and isobaric. We're going to define a flash, which is a function of z, the pressure, and the temperature. The vaporization pressure is equal to P dot P vap at that temperature. Remember that this P is the properties up here, and P vap is from within this import. It grabs the vapor pressure for us, which is really nice. K is also that vapor pressure over the system pressure. And this is the code from homework 1 part C and D, just to remind you that this, I already went through how to get the bubble pressure, dew pressure, bubble temperature, dew temperature. So I'm just going to simplify this for us. For this case, since I already went through all of that, the bubble pressure is the sum of the feed composition times the vapor pressure, which we calculated up here. And the dew pressure is equal to 1 divided by the summation of z divided by the vapor pressure. I just referenced something really quick to type this in, but basically is a quick check. I just did a random composition here. I just said 1, so that would be all benzene. And this is 1 bar, 370 Kelvin. And so we can see that this is correct right here. And then it also calculated our bubble and dew pressure for what I gave it. So that's just useful to have printed out for you. And what this is doing is it's literally just taking the temperature you gave, printing it out to confirm that it's correct. It's in Kelvin. And then this right here converts pascals to bar so that we're in bar. And that's essentially what it's doing for us right there. I'm just printing it out. Now we want to ensure that the flash is occurring in the two-phase region. So if phi is 0, we would have our Rachford-Rice with 0.0, z, and k. If our phi was 1, we would have the same thing but with 1. And remember that phi is 0 at the bubble pressure and phi is 1 at the dew pressure. It's just good to keep that in mind. So if our phi 0 is less than 0, we are at a subcooled liquid with no flash, and then phi is set to 0. And then we want to return these values. And then we're going to do elif, which is basically else if phi 1 is greater than 0. We have a superheated gas with no flash, and phi is equal to 1. And that should be another z, actually. And here we would return same thing, but phi is 1. And if neither of those are true, then we have a flash, and it will proceed with the solver. And from above, I'm actually going to take that phi guess that I explained kind of where that came from earlier. Just a guess for what we can start off with phi. And we can print that for us. So as I said, this is the interpolated guess for phi. And we're going to print out phi guess, and 3 decimal places is fine. And now we want to solve for phi. So that is going to be, we are going to use the optimize root scalar Rachford-Rice. Our arguments that we're giving to it are the z and k. Between these values. And this is the method we're using this time. And then to solve for phi, we are taking this and getting the root of it. And then this is what it wanted me to do. So that's fine. And then this should be solved for compositions. You know, x is equal to z divided by 1 plus the phi it solved for times k minus 1, and y equals k times x. We want to what I wanted was we want to return these values. Now we would like to apply our function to the flash calculation for a feed of this 40-60 moles of benzene / toluene at 1 bar and 370 degrees Celsius. So we're going to say that our feed, our z feed, is equal to numpy array of 0.4 and 0.6. That is what this 40-60 moles means. We have 40 benzene and 60 toluene, and again we had these properties pulled earlier. The system pressure is 1 bar, so we need to do 1e to the 5 so that it's in the correct units. The temperature of our system is 370 Kelvin. And I just grabbed this line and copied it from somewhere, but basically what this does is it gives us a line like this so that it kind of separates our print options. So our final phi, our final x, and final y are going to be taken from the flash calculation. So this flash calculation up here ZPT, we are giving it our Z from here, our system pressure and our system temperature. Okay, so one of the most unfortunate things just happened. I think I was talking for probably like 20 minutes, or maybe not that long, but I was walking through this and I wasn't even recording myself. So I'm going to continue from where I believe I left off. Some errors I had, if you saw that I was getting errors when I ran my code, I forgot this multiplication sign right here, so I had it like that. The code doesn't know that I want to multiply those, so I needed that. And I also forgot an equal sign right here, so again, the code did not know what I was asking for. And I just double checked. I think where I left off was here. So I'm going to walk through what I did when I was not recording. So I'm applying my function to this flash calculation described. 40% benzene, 60% toluene at 1 bar and 370 Kelvin. So we set our feed right here, our system pressure to 1 bar and our system temperature to 370 degrees Kelvin. This print right here, and it creates an enter with this N, and then 40 equal signs, just to kind of divide things up a little bit visually. And then here we're saying that the final phi, x final, y final all come from this flash, and we are running the flash with the Z feed, P system, and T system given. And then we print the final flash results. The vapor fraction is phi final. This is 3 decimal places. I'll keep this consistent, so I'll do 3 decimal places for these guys as well. And I'm going to get rid of these prints since I'm doing it later on. I guess I can keep that one, that's fine. So hopefully I covered everything that I thought that I was recording earlier, but basically we have our system check at 370 Kelvin and 1 bar. It calculated that for our given feed, the bubble pressure was a bit above the system pressure and the dew pressure is a bit below the system pressure. And so since the system pressure is between these two, we can do a flash. Our interpolated guess for phi was pretty close to our solution, so that's not a bad thing to do if you need something really fast, but obviously this is going to be a lot more accurate. And our vapor fraction phi is up here as well, but 0.297. The liquid composition of benzene and toluene is seen here, which is actually pretty close to the feed composition. And then the vapor composition is right here. As you can see, benzene is a bit higher than toluene. That's because it's more volatile. So yeah, in this video we went through, explained and derived the Rachford-Rice equation for vapor-liquid equilibrium, showed that it is a monotonic function of the vapor mole fraction, that phi, and then we implemented this into Python, made sure that the flash occurs in the 2-phase region, and explained how we can use those bubble and dew pressures to get an initial guess of phi. It was pretty close, not too far off, but still we wanted to apply our function to the flash calculation to get that calculated phi value, and we did that. So part B, we are going to go into a more non-ideal situation with NRTL. NRTL is the non-random to liquid model. So it's an activity coefficient model that we use to calculate phase equilibrium. As always, thank you for watching, and part B should be out super soon, so look forward to that.